Good morning. This is the video for 91, 92, and 93. Let's do it. 91 says, Jason wants to determine how the age and gender are related to a political party. The voter list is stratified by gender and age group. Jason selects a simple random sample of 50 men in one age group, 20 to 29, so 50 men in their 20s, and records their party registration, Democrat, Republican, or neither. Then he selects an independent simple random sample of 60 women in a different age category in their 40s. Of the following, which is the most important observation about Jason's plan? So right off the bat, I made a quick table here. It says the data he collected, men in their 20s and women in their 40s. And he's comparing Democrat, Republican, or neither party. And he's talking about 50 he talked to from this group, 60 from that group. And right now, we're really thinking to ourselves, if I'm specifically only looking at these groups, then the only information I can say or make an inference about are these specific groups. So there seems to be right off the bat, this is not really a design we've ever seen. So they're wanting us to look into what could be wrong with this. So it says the plan is well conceived, good to go. It's a little weird. The plan, the sample too small. 50 people, 60 people, you're probably going to get at least 10 yeses and nos. So usually that should be fine. He should have used equal sample sizes. So that doesn't matter. As long as you get at least 10 yeses, 10 nos, you're good to go. He should have randomly selected two age groups instead of choosing them non-randomly. Not sure where they're going with that. What I'm really cluing in on is where I feel like the study went wrong is it says he's not going to be able to tell the difference of whether it's a party affiliation question or it's just the difference in age. So let's say he gets a whole bunch of Democrats in the man group and a whole bunch of Republicans in the female group. Is it because their men vote differently than women, or is it because of their age? Because he's not comparing men and women of the same age, he's not going to be able to tell the difference. And that's what that E is saying. Next question. 92, this is exactly the same as a previous question. So let's hope most folks got it right this time. AP statistics is our formula, and we know to find the residual, it looks like this. AP, but without the statistics. The residual, or RAP, the residual is the actual minus what we would predict. So using this formula, this is my predictometer. Using the formula, I can plug in an X value, and I get a predicted Y value. And I did that. I used this X value and put it in the formula and got that Y value. So my Y hat value here, when I plugged in 20, was 29.6. And so that's what I would predict I would get. But what did I actually measure? And it said actually a 20-month-old has an actual weight of 25. So therefore, the actual amount, 25 minus 29, notice I get a negative residual, and I'm cluing in on the fact that I knew both were going to be negative, so I can eliminate C, D, and E because I know automatically I predicted something heavier, and this child was less than I predicted, so the residual was negative, and my actual value, this would be the best answer, negative 4.6. 93, this is a doozy. If students don't get this question right, no harm done. But it does give us an opportunity to have a discussion about what this means. So the T distribution is symmetric. So I need my formula card. The T distribution is symmetric. So I go to table B and I look and I say to myself, aha, this picture is the T distribution in table B, and it totally looks symmetric. So I really like 1. So I go down here and I say 1 only could be true, not that one, not that one. And I look, so right at this point, I've eliminated B and C. Now let's keep reading. Item 2 says the T distribution of K degree of freedom has a smaller variance than the T distribution of K plus 1. So there's nothing really I can do here other than try to plug in numbers. So I looked at this same table, my T distribution table, and I just made up a degree of freedom. So I put, okay, what would be the T distribution with a degree of freedom of 5? And I came up with a value. I noticed that inside the table it said 0.727, and the next value said 0.920. And I'm noticing that the difference between those numbers is 0.93. So the variability between these two numbers is 0.193. Then, just like the question says, would the T distribution of K plus 1 degree be different? So adding the number 1 to 5, I get a degree of freedom of 6. And now I'm looking at the table and I see 0.718 and 0.906. So when I compare those amounts, it looks like the difference, or the amount these are varying, is a little smaller. So when I made the degree of freedom go up by 1, the variability got smaller, and they're saying that the degree of freedom, the K degrees of freedom, has a smaller variance than the K plus 1 degree of freedom. And that's actually the opposite of what I found. I actually found that the first one is larger than that one. So the one for 5 is bigger than the one for 6. So I wrote in larger. Now that I know that 2's bad, I basically am limited to either A or E. Now I read this and I kind of take a leap of faith, and it says the T distribution has a larger variance than the standard normal distribution. So I look at my standard normal, and I know that the variability of my standard normal, or my z-score goes from 3 to -3. That's pretty much as far away from the mean as I get on a z distribution. And that I just get right off of my z table. All right, you can see in here, my z-scores tend to go from +3 to -3. That's my variability. So when I compare that to my T-chart, on my other page, they're saying the T-chart has a larger variance and it does appear that that is true. So my answer here is E. 1 and 3 are correct. Thanks for joining us.